Infinite limits. If the title didn't give it away, this lesson will deal with infinite limits. This will be the first way infinity will be used with limits. These limits will have an answer that is either positive infinity or negative infinity. In a previous course, you may have learned about vertical asymptotes and learned that as a graph of a function approaches a vertical asymptote, that it will increase to infinity or decrease to negative infinity. In this section, we will evaluate limits a little bit differently to find the answer. Consider the following. Here we have a limit as x approaches 0 of 1 over x. Now, if we were to look at this graphically, 1 over x would give us this graph right here in red. It is the reciprocal function. Now, at the moment, we can totally break this down into two different limits. We could first try to find the limit as x approaches 0 from the left of 1 over x. And we could also try to find the limit as x approaches 0 from the right of 1 over x. Now, in doing so over here, just looking at these limits, if we try to substitute 0 right in for x, that gives a 1 over 0. And anytime you're left with a non-zero number over 0, that means this limit does not exist. But it does not exist in the sense that we cannot call this limit. We can't say that this limit exists in the real numbers. So we can't call this answer a real number. We have to call it something else. We'll get to that in a minute. And if you look at this other example down here as x approaches 0 from the right, when you try to directly substitute numbers in, the number in, you'll end up with 1 over 0. And again, this limit does not exist, meaning we cannot give a real number for an answer. So instead over here, we're going to look at the graph and notice that as x approaches 0 from the left, the graph goes down and it keeps going down forever. Going down forever would be negative infinity. So now we can write the limit as x approaches 0 from the left of 1 over x equals negative infinity. And by the same train of thought, we can say the limit as x approaches 0 from the right of 1 over x is positive infinity. That's because as we approach the 0 from the right, the graph here goes up forever. That being said, we can find out finally the limit as x approaches 0, the two-sided limit of 1 over x. This limit truly does not exist because these answers, all be they infinities, they still need to match for a limit to exist. On this slide, we will take a look at some examples of limits that approach vertical asymptotes. In this first example, we have the limit as x approaches 2 from the left of 1 over x minus 2. Again, the first thing you want to try is substituting the number in for x, and that gives you a 1 over 0. And that lets you know that the answer will end up being a positive or a negative infinity. Now, in order to get this answer, we need to use a little bit of logic. As we're approaching 2 from the left, that means we are looking at numbers, we're picking numbers that are less than 2. And if you substitute those numbers that are less than 2 in for x here, you will end up with a negative fraction. So we can think of this as a 1 over 0 from the left. And you saw from the previous slide that a 1 over 0 coming from the left gives you a negative infinity. All right, there's the answer. In the next example, there is a limit as x approaches 2 from the right of this same function, 1 over x minus 2. So similar idea, we can substitute the 2 in, and we will end up with a 1 over 0. But again, since these numbers, since we're approaching x from the right side, all of these numbers are bigger than 2. So the fact that they're bigger than 2, numbers bigger than 2 take away 2. That means we would be approaching this 0 from the right. And that gives you, from the previous slide, 1 over 0 from the right is a positive infinity. So there's the answer for example 2. And again, in example 3, the limit from the left is negative infinity. The limit from the right is positive infinity. These two things do not match, so this limit does not exist. All right, in the fourth example, the limit as x approaches negative 5 from the left. So we can substitute the negative 5 directly in for these x's. And in the numerator, that's no problem. In the numerator, that gives you a negative 6 over, and in the denominator, you end up with a 0. So this 0, let's see, using the logic, negative 5 from the left, that means there will be numbers less than negative 5. So if you have numbers that are less than negative 5, this entire denominator becomes negative, which means we would be approaching 0 from the left. Approaching 0 from the left means this would be negative infinity. However, there's a negative in the numerator. A negative divided by a negative gives you a positive infinity. In example 5, you can see that the limit as x approaches 2 of negative 2 from the left of x plus 3 over x squared minus x minus 6. The first step here is to double check what happens when you can substitute negative 2 in for all of these x's. When that happens, you'll see that you get a 1 over 0. Again, that non-zero number over 0, that tells you the function is approaching a vertical asymptote when x approaches negative 2. So we substituted the negative 2 in for all of these x's. We ended up with a negative 1 over 0. And since the function is approaching, or the x's are approaching negative 2 from the left, if you substitute numbers in to the left of negative 2, this denominator will end up being positive. So this would be a 0 from the right. So a positive 1 over 0 from the right tells you the limit will approach infinity. In example 6, we have the limit as x approaches negative 1 from the right of x minus 2 over x squared minus 1. And again, I think you see the pattern. You substitute the negative in for top and bottom, and you end up with negative 3 over 0. So now after you substitute that in, you will want to check that what happens with the denominator as x approaches -1 from the right. So with numbers close to the right of -1, if you substitute that in here, you'll end up with values. When you square something that's less than -1, you'll end up with a value that is less than +1. And so when you have a positive number less than 1 and you take away 1, you'll end up with something that is negative. And you know that if you are coming at 0 from the left, that is -infinity. But a -infinity under a -3 turns it into a positive infinity, because a negative divided by a negative is in fact positive. And in this last example, the limit as x approaches pi/2 from the right of secant x. Now this one is interesting because it looks like you can just substitute this pi/2 right in for secant x and get something. If you think of it a little bit differently, if you remember that secant is 1 over cosine x, this will allow you to see that when you substitute 0 or pi/2 in for x here, you'll end up with 1/0. Now since the x is approaching pi/2 from the right, if you think about the graph of cosine of x, it does something like this, and here is pi/2, and you are approaching it from the right. All of those values are negative. So approaching 0 from the right means -infinity, and since it's underneath a +1, this answer will in fact be -infinity. Vertical asymptotes, or abbreviated VA. The line x = c is a vertical asymptote, it's a definition, of a function f if either 1. The limit as x approaches c from the left of f of x is either positive or -infinity. 2. The limit as x approaches c from the right of f of x is either positive or -infinity. Or 3. Both of these things. Let's take a look at this a little deeper in pictures. So in these 3 pictures down here, you can see all 3 scenarios. The first, the limit as x approaches c from the left of f of x is either positive or -infinity. And in this case, this graph goes off to positive infinity as it approaches c from the left. The other half of the function can basically do whatever it wants. We've already established that there's a vertical asymptote here because this left side, as it approaches the c value, it's going off to positive infinity. In the second one, in the second case, the limit as x approaches c from the right of f of x equals ±infinity. So it just has to be one of these two. It doesn't have to be positive and -infinity. That doesn't make any sense. So you can see that this graph from the right side approaches -infinity as x approaches c. Again, the left side can be doing whatever it wants. We've already established that there is a vertical asymptote from the right side of this graph. And then the last example, both 1 and 2, that means as you approach c from the left and from the right that the graph approaches positive or -infinity. And in this case, both of them are going to infinity. So this establishes that there is a vertical asymptote at x = c. On this slide, you will see a couple examples for finding vertical asymptotes for functions. There are three steps you should follow when trying to find vertical asymptotes. They are over here on the right. The first step is you want to factor, and you'll want to factor the top and the bottom. Then you'll want to simplify the fraction or cancel any factors that cancel. And the last step is to set the denominator equal to 0 and solve. So in this first example over here, what we want to do first is factor the top and the bottom. So when you do that, you will get something that looks like this: x minus 6 times x plus 1 all over x plus 1 times x plus 2. Step 1, check. Second step, simplify. You can see that in the numerator and the denominator, there's a common factor here of x plus 1. Let's reduce those away. And so we have simplified this function to be x minus 6 over x plus 2. And lastly, we can set the denominator, x plus 2, equal to 0 and solve for x. This leaves us with x equals negative 2. That is the vertical asymptote for this function here. And just as a note, if you go back and look at the definition of what a vertical asymptote is, as the limit, if you look at the limit as x approaches this value, negative 2, of the function x squared minus 5x minus 6 all over x squared plus 3x plus 2, we already know that simplifies to the limit as x approaches negative 2 of x minus 6 over x plus 2 via this simplification up here. And if we look at the limit more specifically as x approaches negative 2 from the left, then we know that we can try directly substituting this negative 2 in for x, and we will get something of the form negative 8 over 0. And here it is, that non-negative number over 0 lets you know that as x approaches negative 2 from the left, that the function will be approaching infinity or negative infinity. And since x is approaching 2 from the left, we know that the denominator will approach 0 from the left, which means we will have a negative 8, and approaching 0 from the left means negative infinity, so negative over negative gives you a positive infinity. So going back and looking at the definition of what a vertical asymptote is, as the limit approaches some value from the left or from the right, or both, if you get an infinity, then there is, or negative infinity, then there is a vertical asymptote at that value. You will not need to go through and show this every time. These steps over here are what allows us to find the vertical asymptotes. In the next example, you can see we have g of x equals x minus 3 times x plus 1 over x plus 2 times x minus 3 to the 4th. And it looks like an x minus 3 will cancel, and this fraction simplifies to x plus 1 all over x plus 2 times x minus 3 cubed. And now if you set the denominator equal to 0, or each factor in the denominator equal to 0, you'll get x plus 2 equals 0, which tells you x equals negative 2. So there's a vertical asymptote at x equals negative 2. And if you take the x minus 3 cubed equals 0, well, you can take the cube root of both sides to get x minus 3 equals 0, and then you can take add 3 to both sides and get x equals 3. So here is another vertical asymptote for g of x, and together there are two vertical asymptotes for g of x. On this slide, one more example on finding vertical asymptotes. The first thing you want to do is find the discontinuities, and that's what you want to do because you'll notice this example is different from the previous two because this is a piecewise defined function. So the first thing I want to do is first find out where is this function discontinuous. That's exactly what we were doing in the previous two examples, finding out where the discontinuities were. So if you look here, there's a possible discontinuity at x equals 1. And we get the same thing here, that there is a possible discontinuity at x equals 1. So let's use the definition of continuity to see if that is the case. We need to know if h of 1 exists. And yes, it does exist because when x is 1, down here in the bottom, x is greater than or equal to 1, we can directly substitute that 1 in here. 3 times 1 plus 2 gives a y value of 5. So yes, h of 1 exists. We need to check that the limit of as x approaches 1 of h of x exists. And let's see, since we have a piecewise function that is broken apart at x equals 1, we should probably check the limits as x approaches 1 from the right of h of x and the limit as x approaches 1 from the left of h of x. And then we really need to check, are these things the same? This question mark above the equal sign, we're trying to figure out, are these two things equal? So we already figured out what happens here with this limit as x approaches 1 from the right. That was done right here. So that equals 5. No problem. We just need to figure out what happens when the limit as x approaches 1 from the left. That involves this other function because x is less than 1. So we're taking the limit as x approaches 1 from the left of 1 over x minus 1. And if you substitute in that 1, you'll end up with the form 1 over 0. And we're still trying to figure out whether these two things are equal. So we have this form over here, 1 over 0, non-zero number over 0. That means that there will be a vertical asymptote at x equals 1. And since the function is approaching x from the left, that means these numbers will be less than 1, which means all of these numbers in the denominator will end up being negative. So that'll be a negative infinity. And it turns out that 5 is not equal to negative infinity. So the limit does not exist. No, the h of 1 exists, limit does not exist. And in showing that this limit does not exist, we also showed that from the left, there is a vertical asymptote at x equals 1. So there is a vertical asymptote at x equals 1.